I'd like to first thank Microsoft Research, Nankai University, and Tianjin University for hosting this event. So thank you. It's a real honor to be here in this beautiful city of Tianjin with lovely weather today. So I really am looking forward to giving my talk to all these eager, energetic young students in the audience to share my new ideas and new questions. I'm going to talk about a theory of trust, towards a theory of trust in networks of humans and computers. And the talk I'm going to give is going to ask more questions than answer questions. And this is, I think, especially appropriate for this audience. It's going to point to new fundamental questions in security that I think challenge all of society today. So let me start. I'm motivated by actually a problem that Manuel Blum, a Turing Award winner, asked a couple of years ago. We have to recognize, especially appropriate in the theme of the 21st century computing naturally, we have to recognize that the computer of today is very different from the computer of yesterday. The computer of today actually is made up of humans and machines. We have now networks of humans and computers that are solving problems that neither can solve alone. So this is the computer of today. And one could ask some deep scientific questions in this context. What is computable by such a network of humans and computers? But I'm going to focus on a different question. And this question is, how can I, as a human being, trust the information that I read over the internet? A very common situation is we go to our machine, we look something up in Wikipedia, and we read what is displayed. Why should we trust what that Wikipedia page says? That's the question I'm asking. And in trying to disentangle this question, we will see in my talk many questions that are unanswered, many problems in computer science that we still have to answer. But probably the most important part of my talk is that it's not just about computer science. The most important part of my talk is that to answer this question, we have to bring in the social, behavioral, and economic sciences to understand a broader theory of trust in this context. So the insight is that computational trust defines trust relations among devices, computers, and networks. Behavioral trust defines trust relations among people and organizations. And a theory of trust for networks of humans and computers needs to include elements from both. So let me decompose the question. How can I, as a human, trust the information I read over the internet? Let me associate messages that I receive over the internet as information. And let me associate receiving messages as what I read over the internet. And so we're in a more familiar territory now when we're talking about receiving messages. And now let me decompose the question into two questions. One is the communication channel over which I receive messages secure? The second is, how can I trust the sender of the messages I receive? Or another way to put this is, how can I trust the person who wrote that Wikipedia page? Why should I trust the site that hosts that page? And so on. Let me start with a simple communications model, because this will let me get rid of the first question and put it aside. So we have a sender and a receiver. Sender will always be on your right. and the receiver will be Bob, and he'll be on the left. We're going to assume that we have secure, private, available channels. We're going to assume that we have the computer science technology and the computer science to discharge this assumption. We're going to assume we have a trusted path between the application or the user and her machine, and a trusted path between the receiver and his machine. And we're also going to assume that between the computing devices that are communicating with each other, that there are penetration-resistant interfaces. This means that I basically have secure communication. And so I can gray out the first question of, is the communication channel over which I receive messages secure, because I'm going to assume that I can implement all those properties I just mentioned on my previous slide. That leaves the second question. How can I trust the sender of the messages I receive? So that's what I'm going to focus this talk on. And we'll see that this question, the main question, boils down to the act of trusting the sender, where you should think about the sender as some person or some organization. Okay. Why, let's say I'm the receiver, and why do I even want to ask this question? The reason is there must be some value for me as a receiver to want to interact with some sender. I must be gaining something from this interaction and be willing to risk some cost for having this interaction. Otherwise, I can just not interact at all with anyone. And then I don't have to trust anyone. So there must be some value gained by the receiver in interacting with the sender. And this value must outweigh the cost. So that's what this slide is supposed to indicate. The value underlying the act of trusting the sender. If the receiver trusts the sender and the sender is trustworthy, then value is gained for both. So I gain information, and the sender monetizes on my click. If the receiver trusts the sender and the sender is untrustworthy, then the value gain must outweigh the cost to engage. So the receiver risks getting malware, for instance. But I take that risk because I think I'm going to get some good information. And finally, if the receiver suspects the sender is untrustworthy, then I won't engage. And then no value is exchanged. So these are the ways to think about the axioms underlying this theory of trust. So let's first start talking about computational trust. How do we build trust in the computational elements in our system? And then I'm going to talk about behavioral trust, because we'll see that even if we could do the best job possible for ensuring computational trust, we still need to rely on something else to trust the sender. So the elements of computational trust are isolation, correctness, and recovery. These are all familiar kinds of properties that we study as computer scientists. And these isolation is when a receiver could isolate himself from any sender. So regardless of what the sender is, or who the sender is, or what message is received. We'd like to achieve that, because if you can achieve that, then you can trust anyone, and you can trust any input. But we'll see it's hard to achieve. Correctness means independent verification of the code that the sender might send. Somehow, parts of certain messages might be code, and we actually might want to verify properties of that code. And we know in computer science ways of doing that verification. And the third is recovery, where it may be that we receive a message and we get into a bad state, and we have some way of recovering back into a good state. And again, in computer science, we have techniques to default recovery, and so on. So we'll see that all of these elements are necessary for providing computational trust, but they're not sufficient. So let's just look at the first one, isolation from the sender. So we have one way to possibly isolate ourselves from the sender is verify any input message that we might receive. And as I said, if we can verify any input message that we can receive in terms of the properties and the behavior of the code that might be in there, then trust of the sender is not needed. However, let's look at how possible is isolation from any sender. Can input always be verified? Well, the input might be anything from a piece of text or to a piece of code. So, no, arbitrary code cannot be verified. I might ask the property, for instance, does this piece of code that I just received halt? And we know we can't do that. We can't answer that. Suppose the input can be verified. Is verification always efficient? Well, no. It might be that the message is a solution to some co-NP problem, and we know that verifying the solution will be inefficient. Suppose the input is, we can verify it efficiently. Is it always practical? And again, there are recent results by Parno, actually an ACM dissertation award winner from Carnegie Mellon, who's now at Microsoft Research, who shows that it may be possible to, for instance, send a piece of encrypted code over to a server, say Microsoft Bing, that might, say, do a search over a large database of pages and send back a result that the receiver can check really quickly. So we know we can do this. However, to do it is not quite practical yet because these kinds of techniques rely on fully homomorphic encryption, that technique is not quite practical yet. But it gives you a hint at what might come in the future. Okay, suppose input verification is efficient and practical, and is it always scalable? Even here, the answer is unfortunately no. And we have security models from decades ago, the mid and late 1970s, that have come up with ways for us to define how we can check certain conditions on input messages with respect to a particular security model. The problem is, in the internet today, not all organizations and entities and individuals buy into a single security model. So not one security model fits all. Okay, so now we're in the situation, isolation from the sender is hard. Suppose the sender can provide evidence of trustworthiness. So now we can't, when the receiver really needs to interact with the sender, and the sender is going to promise to send over not just the message, but some evidence that what is in that message should be trusted by the receiver. So this is the situation. And here, the hardest example is when the message contains a piece of code. And so we might want to ask about how to verify that piece of code with respect to certain properties. And the situation is, if we have complete sender trustworthiness, no isolation is needed, and the input can always be accepted. And you'll see that we still can't do this. So for instance, is it practical? Not usually. Code correctness proofs are not scalable. They're first often limited to small configurations or limited to a few properties. So I might, for instance, pass a piece of evidence would be a proof that the code is correct with respect to a specification, so that I can, as a receiver, check the proof. But this kind of proof-carrying code is often restricted to certain kinds of properties. Another problem with scaling this technique is that the techniques we use to do the correctness proofs themselves are often human-intensive. They often require interactive theorem proving. So the real problem with, even if we could do full verification of code and provide a proof or evidence that that code is correct, is that that code might still have some input parameters uninstantiated. So somewhere, someone, or something is going to instantiate those input parameters. So we still have some reliance on that someone or something. So how do we do it today? We rely on reputation services, third-party recommendations, outsourcing trust relations to get a sense of whether the human is trustworthy or not. And I think this should give you a hint as to what is going to come in terms of the behavioral trust we need. So providing complete or irrefutable evidence that the sender is trustworthy is hard. Suppose a receiver can detect and recover from a sender's untrustworthiness. Okay, so in this case, we get an input message, we get ourselves into a bad state, and we figure out, we detect that we're in a bad state, and then we need to recover from this to get ourselves into a good state again. Is this feasible, practical, and scalable? By the way, all of these seemingly challenges are great questions, research questions for you to be thinking about. So the answer is no, not usually. It might be possible in certain situations. For instance, a lot of the work in fault-tolerant, distributed, transactional databases have figured out how to do this. That's why we can go to an ATM machine and do transactions online. However, there are situations where it is impossible to undo the effects. The standard example is, in fact, when you go to the ATM machine, you withdraw money, and then you can't undo that. You're hardly going to give the money back. So that's an example of I/O where those effects cannot be undone. Okay, so we're in a situation where we can't have isolation from the sender, we don't have sufficient ways to provide trustworthiness evidence, we can't always recover from bad input. Well, suppose when we do get bad input, we punish the sender. So here what we need is, if we want to have deterrence, we need punishment, and for punishment, we need accountability. So what that means is, if I do want to punish the sender, I need to know who to punish. This is well known, this sort of implication, the necessity chain. But we also need sufficient punishment to deter and sufficient accountability to punish. So this is actually a new idea. Okay, is deterrence always practical and scalable? And here, no, not always. What deters human behavior, or what deters human misbehavior, is an outstanding question that has been debated by the legal community for centuries. So let me just summarize where we are in terms of the act of trusting from a computational point of view. We don't have this, isolation from sender. We don't have a way to provide complete, irrefutable trustworthiness evidence. We can't always recover from bad input. We don't have complete ways of deterring people from sending bad input. So, but this is, of course, the internet of today. So is there ever a way that we can ever be safe to trust the sender? And this is where the new idea of combining elements from behavioral trust from the social, behavioral, and economic sciences come in. So let me just tell you right now, in terms of the theory of trust so far, in terms of the computational elements. We've got cryptography, verification, fault-tolerant computing. All of these have been studied for many years to provide elements of computational trust to give us secure communication, ways to do isolation, ways to prove programs correct, provide sender trustworthiness, and do recovery. But we need more. We need to define trust among humans. And so what we're going to do is look to the social sciences, where they have studied this question for many, many decades. The act of trusting, what should the act of trusting mean? And hundreds of research articles have been published on this very topic, but not in computer science, in economics and social science. So we should, as computer scientists, be looking outside of just what we understand about security and computing and looking to what these other sciences have developed in terms of theories of trust. And so that's what I'm going to explain in the next few slides. There's a notion of behavioral trust specifically that I'm going to give an example of. And this notion of behavioral trust says axiomatically that there are beliefs and preferences, and that's all there is. And that's quite a powerful statement. So let's just look at a single model for behavioral trust. I'm taking this from a paper by an economic scientist, Fair. The sender is now going to be, I'm going to call that sender a trustee. So it could be the bank, eBay, Google, Amazon, Microsoft, some third party that you trust. You trust the bank with your money. You trust Google with all your information, and so on. The receiver is the trustor. So I'm the one, say, bidding on an auction. I'm the one consuming some information. I'm the customer of a bank. And the model is going to be based on a one-shot game. And so what I'm going to do in the next slide is explain what a one-shot game is. So there's a dealer, and there's a sender and a receiver. And the dealer gives $10 each to the sender and $10 to the receiver. And the game is, as the receiver, I get this $10, and the rule is, if I send my $10 over to the sender, the dealer will multiply my $10 by 4. So that means the sender would receive $40 from me. In case one, if we cooperate, there's a win-win situation. So if we cooperate, I send my $10 over, the dealer multiplies my $10, the sender gets $40, and his responsibility is to take all the money he gets from me and from the dealer and divide by 2 and send me the other half. So in this case, the sender gets $10 from the dealer, $40 from me, that's $50. Divide by 2, that's $25. And the sender, if in the case of cooperation, sends me back $25. So I sent the sender $10, and I got back $25. So as a receiver, I get $25, gaining $15. And the sender keeps $25, also gaining $15 over what the dealer sent. So this is the win-win situation. Now, of course, there are other cases. So for instance, I could send my $10 over, and the sender might decide to keep my $10, and I lose. So I get $0 as the receiver, I lose $10, and meanwhile, the sender keeps $50. So the sender gains $40. That's not really nice, but that's case 2. Case 3 is I might decide I don't want to play this game. So I get my $10, and I'm not sending over any money, and the sender gets his $10, and nothing happens. In this case, by my not sending over $10 to the sender, there's a part of me that says, I don't trust that sender. And so no trust, no value gained. And the same thing is true on the sender side. No trust, no value gained. So this is an example of a one-shot game. And these games are used in spades in economics and social science to try to understand human behavior, to try to incentivize certain behavior. So this is just a very simple example to tease you into thinking about what trust might mean. Before I go on to the next part of the experiment, let me just show that the possible value outcomes of this game are analogous to what I talked about before in terms of senders and receivers gaining value in interacting with each other. So in the game example of the trustor trusts the trustee, and the trustee is trustworthy, then the trustor and the trustee are better off before executing the protocol. Cooperation pays off. If the trustor trusts the trustee and the trustee is untrustworthy, then the trustee is better off and the trustor is worse off. That is, the trustee has strong incentive to cheat in the absence of a mechanism that protects the trustor. And then, of course, the third case was if the trustor suspects the trustee will cheat, then he's not going to engage. And thus, no value is exchanged. And this is completely analogous to what I said earlier in terms of the sender and receiver interacting in networks. Okay, so in fact, this one-shot game has also been used as the basis of some human experimentation to understand, to tease out some of these elements of behavioral trust. I already mentioned the two main ideas are beliefs and preferences. But in fact, there are two different kinds of preferences. And this game that I'm going to explain, this experiment I'm going to explain, teases out those two kinds of preferences. So the continuation of the game is the dealer has 20 punishment units that he gives the receiver. And there are 3 different cases of how the receiver might punish the sender. So in the first case, it costs the receiver to punish the sender. So if I find out that the sender cheated on me, then if I want to punish the sender, it costs me one punishment unit. And the sender then is punished by 2. So it costs me something to punish the sender, but the sender is doubly punished more than me. That's the first case, so that's the cost model. In the second case, it's free for me to punish. It doesn't cost me anything. And the sender is still punished by 2 units. And in the third case, it doesn't cost me anything. It's just symbolic that the sender is punished. So that doesn't cost me anything, and the receiver is not punished by any dollar amount either. And it turns out that this is human behavior now that we're measuring. Most receivers pay the dealer to punish cheating senders. So first of all, this experiment had 15 subjects. So one subject didn't even want to play the game. Of the 14 subjects, 12 subjects were willing to pay to punish the sender in the cost model. But everyone, all of them, were when it was free to punish, wanted to punish the sender. And then in the symbolic case, not so many receivers felt like they really needed or wanted to punish the sender. So now let me tell you about yet another case that was part of this experiment. And this will make a distinction between two kinds of preferences, what's called risk preferences and betrayal aversion. So, in fact, in this experiment, the subjects, the human subjects, were monitored, their brains were actually monitored. So PET scans were taken of their brains as they were playing this game. And it turned out that there's certain parts of their brain that are known to be associated with reward satisfaction. So it turns out that the PET scan of the receiver's brain showed reward satisfaction when the receiver punished the sender. So this is called betrayal aversion, the aversion to being scammed or cheated. And the reason that in this experiment and in this theory of trust for humans, the reason that people in the social science and economic sciences studied this was to be able to make a distinction between betrayal aversion and risk aversion. And so the fourth experiment that was run was when the sender was not a human. The sender was a computer. And the dealer would tell the receiver, oh, well, you didn't get your money back, but it was just a random process that kind of randomly decided whether he would send your money back. And so in this case, the receiver didn't feel like, punish a computer? The receiver didn't feel like he really needed to punish a machine, as opposed to punish a human being who cheated on him. And so in this fourth case of the experiment, there was very little desire to punish, and thus no little or reward satisfaction. Interestingly, your brain can be chemically altered to control betrayal aversion. So again, this is very interesting to me when I read the literature that the social sciences actually run these experiments on humans and do try to chemically alter the brain to measure the degree of betrayal aversion. And again, this is very distinct from risk aversion. So let me just summarize the experiment's results. The truster or the receiver is willing to incur a cost to punish, and the amount of punishment inflicted was higher when the punishment was free. The truster or the receiver derived satisfaction, felt rewarded, proportional to the amount of punishment inflicted on the cheating sender. And finally, when the truster or the sender is replaced by a random device, like a computer, then the receiver's desire to punish was negligible. So what we have is a theory of trust for humans based on beliefs and preferences. And there are two kinds of preferences: risk preferences and social preferences. So in terms of beliefs and trustworthiness, this is usually measured in terms of probabilistically, and that's just the probability that I'm going to play the game. So 1 out of 15 people didn't play the game. In terms of risk preferences, this is really noting that when the machine was a sender, the degree of risk aversion was low. And then in terms of betrayal aversion or social preferences. If the cheater was a human and with the sender was a cheater and a human, then the receiver really felt like punishing. Okay, so I'm going to wrap up. What I'm really trying to argue is there's a new way of thinking about trust in this world of networks of humans and computers. And it's not sufficient to look at just computer science to understand this notion of trust. We need to look to other sciences that have been studying trust among humans and organizations for decades. So we have a notion of beliefs in senders, trustworthiness, we have preferences and aversions that are either risk or betrayal. We have counterparts to this in the computational world. The interesting question for us now, if we understand this theory of trust about humans, is how do we bring this into the computational realm? How do we invent computational infrastructure and computational mechanisms to actually support these theories that include beliefs, risks, risk aversion, and betrayal aversion? So that's really the punchline. We already have some hint that some techniques that we have from Proven Code Correct will help provide trustworthy evidence that might have something to do with beliefs in the sender's trustworthiness. With respect to risk, this is, well, if something bad happens, you try to recover from what's bad, so maybe we can recover from sender noncompliance. But the really new idea to both the social science community and the computer science community with respect to this question of security and trust is what is out there in terms of computational mechanisms and computer infrastructure to give us the support for detecting betrayal and punishing the sender, and even or deterring the sender from betraying, or figuring out accountability so that we would even know who to punish. And so we have, in practice, ways that are practical enough for some aspects of correctness, some aspects of recovery, but we don't have, at least from computer science, a serious way of thinking about betrayal aversion. We have things like third-party recommendation services and reputation services. Those are kind of those are ad hoc mechanisms. And what I'm really seeking are more systematic ways of thinking about how to provide a theory of trust that includes betrayal aversion. So this is really what I'm trying to state in terms of people interested in doing research in security. In the past, we built new trust relations derived from old. We had trusted third parties, transitive trust relations, delegation. Today, or in the future, what we're going to need to build are new security infrastructures that promote new trust relations that are possibly unmediated. There's no end-to-end argument. And these are akin to today's reputation services and recommendation systems. And so there's an analogy to transportation, which is even a bigger point that I'm trying to make. And that is, there's a new way that we should be approaching security research. It's not so much there are bad guys and the good guys have to always keep up with the bad guys. It's not so black and white. There's an economics and an ecosystem in this network of computers and humans that we have to be understanding. And so security can bring us new mechanisms that can bring new economic value to interacting with each other over the internet. So the goal is to seek security mechanisms that create new value, not just prevent loss. And that's the close of my talk. Thank you.